All right, so practice 8.1, 8.2. Looking at the first one, and we get a picture here of 4 different scenarios. And looking at momentum. So part A wants to know the momentum of system A. And we got these velocities. So system A. Whoops. Bringing my paper closer to my hand instead of make my hand closer to the paper. So looking at A, we have a mass moving to the right. Do we know these masses? Yes. So we have a 5 kilogram mass, and that is moving to the right. And that velocity, 3.16. So a little bit awkward. They're giving us the mass up here in the picture, but then they're giving us the velocity down here in the statement. So mass 5 kilograms, moving to the right at 3.6, so that's going to be positive. We'll use a standard coordinate system. That moving to the right is positive, so standard coordinate system. And then looking at the other mass, which is 3 kilograms, so our other mass there is 3 kilograms. And I guess I'll call that 1, 1. We'll call this 2 and 2. And this velocity is also moving to the right, positive, at 8.4. So when we look at the total momentum here, we're going to have mass 1 v1 plus mass 2 v2. And the mass is so what they're really looking for here in this problem is when you will choose the velocity to be negative. So in this case, our velocities for part A are both pointing to the right, so both velocities are positive. And so I have both my velocities as positive. All this will just add together. So looking at part B, they want now situation B in our picture. And we just look at situation B. So in situation B, the first mass is positive velocity, but notice the second mass has a negative velocity. So looking at momentum, we're going to have m1v1 plus m2v2. That first, oh, did they change? They did change the mass values. A little bit unfortunate. So looking at the picture, mass 1 is now 6, and that velocity is 1.6. So looking at the problem here, 1.6. And then mass of the second one is 3 kilograms. But this velocity here, you can see, is moving to the left. So I'm going to put a minus sign in there for my velocity in the second mass. And we got to scroll down here and see that that second mass is 3.2. So here's what I'm going to put into my calculator with the minus on the 3.2. And that gets us 0. Part C. Take a look at part C. Part C, the first mass is positive velocity, but the second mass has a negative velocity. So looking at part C, again, the masses have changed. So the mass of 1 is 9, and its velocity, we got to scroll down here. Velocity is 3.6. And then the mass of the the second one here is 6. But this velocity here for C, that velocity is moving to the left, so that's a negative. I'll put my minus sign in there. And then scroll down and see what that number is, 8.4. So an overall minus 18. And then looking at part D. Part D has 3 masses. The first mass is 7 kilograms, and it's moving to the right. So let me scroll down and see what D is. It's 1.6. Our second mass is 8 kilograms. But this one's moving to the left, so I'm giving it the minus sign because this second mass is moving to the left. And let's see what that velocity is, 5.6. And then the third mass scrolling up is 4 kilograms. And that one is moving to the right, so that'll be a positive velocity. And we'll scroll down and see what that one is, 7.4. And so I'll plug all that into my calculator. We only got one minus there. To get minus 4. Oh, did I punch something in wrong? Let me just check really fast. 1.6, 5.6, 7.4. Did I get all those masses right? I have 7, 8, and 4. 7, 8, and 4. I wrote the numbers down. Let me check my calculator then. Okay. Well, attention of detail error on my part, I would say. Although I think probably many would assume what I just did. So I treated, in part D, I treated this first one as particle 1. I treated this second one as particle 2. I treated this third one as particle 3. That is not what Mastering Physics is doing. This first particle is particle 1. The last particle is particle 2. And the middle one is particle 3. So looking back on that again, so they did a kind of non-standard ordering here. So just to do that again, the first particle is 7. Its velocity was 1.6. Now the second particle they're saying is this one all the way at the end. So that's 4. And that velocity was 7.4. And now oops, I'm sorry, that's not 7.4. That's where I mixed up. This last one, 4 kilograms, are calling the second particle, and the velocity of the second particle is actually 5.6. So it's the 5.6 that goes there, not 7.4. And then if we look, the third particle is actually the middle one, and so that's where we have that 8, and that's where our minus sign is at. But it's not 5.6. The third particle's velocity, if we look at the problem here, the third particle's velocity is actually 7.4. And this is what I have to plug. So these are the two velocities that I switched because of the ordering of how they presented things. So if I go with that new ordering, I get minus 25.6. So I would say ultimately, sure, that's my error. I would call that an attention to detail error. But I would think 1, 2, 3 would be a nice ordering there. But overall, I would say my fault for not paying attention closely to what that little subscript is on these V's here. So that is the last one. We'll check out the next one. So we got another situation of 3 particles, and I hope they do it as a standard 1, 2, 3 here. Let's see. So they do. They have this is A, this one is B, this one is C. So everything is a standard type of ordering you'd expect. And let's take a look. So now we're looking at components. So momentum, X and Y direction. When it's asking for the X component, we're only interested in X direction. So if we look at particle A is completely in the Y direction. It has no X component. We look at particle B, we are at an angle here of 60 degrees. And we need to know that velocity there. And where do they label these velocities? Up here at 10. So here's my right triangle. Particle B has a two-dimensional momentum, meaning a momentum in the X and Y direction. So the momentum here is the X. This would be the X momentum. This is the Y momentum. And then here's our right triangle at 60 degrees with the hypotenuse being 10. So if we want to figure out the X momentum, that's the adjacent leg. Adjacent is going to be cosine. So cosine 60 will get us our adjacent over hypotenuse. So the adjacent there is just going to be 10 cosine 60 for particle B. So this is particle B, where particle A has no X momentum. And if we look at particle C has a momentum to the left. So that mass is 10 kilograms. Ooh, I got to be a little careful. I have to come back to this in a moment. So part C, it's mass, because m times v is momentum. Mass is 10. That velocity is to the left. And let's see what VC is. It's 2 meters to the left. What I have to say about B is this is the velocity. This is the velocity. I still need to multiply this by the mass, which is 6. So let me just say this again. For the X components of momentum, A has nothing. Particle A has nothing because it's straight down. Particle B has momentum of 6 mass times its X component of velocity, which is 10 cosine 60. And then particle C has a mass of 10, but its velocity is to the left at -2. So here's the total X momentum. Particle A has no X momentum. Particle B has some of its momentum in the X direction, 10 cosine 60. And then particle C has all X momentum. And so just typing this into my calculator, and that is 10. So in the X direction, all right. Well, I am making a lot of assumptions here, I guess. They gave us this picture here, and I'm just assuming they were talking about the whole picture. They're not. If we actually look at the question, they just want to know about particles A and C, which means we're skipping B. So we just look at A and C. A has 0 momentum, and then C is just 10 times -2 to get us -20. So they gave us this picture of 3 particles, but part A wants us to actually just ignore the middle one. So it just says right here, just A and C. So again, A, there's no X momentum. B, we're just skipping. And then C has 10 kilograms, and its velocity is -2. So that's this one right here. 10 times -2 is how I'm getting at. -20 for just A and C. Now I'm going to be a little careful. The next question does again say just A, and C. So they're skipping B again. They're skipping particle B. So looking at just the y component of momentum, just the y component. Particle A is all in the y direction. Particle C has nothing in the y direction. So the y direction all comes from particle A. Particle A has mass 5 kilograms. Its velocity is down, so it's a negative. And then where do they list the velocities? They list them way up here. And that's 11.8. So overall, that's a minus 59, just multiplying those two together. Let me look. Part C wants B and C. B and C for C. So they want the x component of B and C. All right, so I'll go back up here. The x component, so now here's where the x component comes in at 10 cosine 60. That's the velocity in the x direction times its mass, which is 6. And then the x component of C, that was the 10 times minus 2, because again, the velocity of C is pointing to the left, so it gets a minus sign. This is what I'll punch into my calculator. To get 10. Now let me check part D. Part D wants B and C only, B and C only, Y component. So let's look, only B and C. So C has no Y component. So C has 0 contribution to the Y momentum. All the Y momentum will come from particle B. And we're looking at the opposite leg. The opposite leg will be from sine. So again, the green arrow has length 10, because that's what they're telling us. They said the velocity of B is 10. And they get the, well, let me draw it here. Just draw us again. They're telling us the hypotenuse is 10. We have an angle of 60. The y component is the one going up. That's the opposite leg of this right triangle. Sine is what will get us that opposite leg. That is the velocity component in the y direction. To get momentum, we'll multiply that by mass. And then here's what I'll punch into the calculator. Well, that rounds to 52. Part E, now what do they want? Now they want all 3 objects. Now they want all 3, which is what I initially did in the starting. Just added all 3 together. That was way back here. Let me just talk about that one again, though, really fast. So part E, x component of all the particles here. So particle A. So we're looking at total x momentum. Particle A has 0 x momentum. Particle B has mass 6, and in the x direction, its velocity is 10 cosine 60, so that's m times vx, the x component. And then particle C is in the minus direction, 10, and its velocity was 2. So here's the total momentum in the x direction of all 3 particles then. And that equals 10. And then finally, the y component of all the particles. So let me go back up and look. The y component of all of the particles. So particle A is all in the y direction. Its mass is 5. Its velocity is into the negative y. And that is 11.8. Particle B. Particle B has mass 6 kilograms. And the opposite leg here is the y component. Opposite we get by doing sign, and that's positive. And then particle C has no y component. So particle C contributes nothing to the y momentum. And then I'll type this into my calculator. And rounding, -7. And that is number 2. Number 3, the speed of the fastest pitched baseball, 45 meters per second, and there's the ball's mass. So they do give the ball's mass in grams, 1,000 grams in a kilogram. So we're going to move that decimal 3 times to get us 0.145 kilograms for that, for the mass of our ball. And part A wants to know, what was the magnitude of the momentum? All right, well, momentum is simply m times v, mass 0.145 kilograms, and the velocity they're telling us is 45. So there is the momentum. So rounding 6.5. How many joules of energy? All right. Well, the energy of motion is 1/2 mv squared. So that means we'll have 1/2 the mass, 0.145. The velocity was 45, but now we're squaring that. So that I'll type that in my calculator. And rounding, that's 147. Part C, how fast would a 60-gram ball have to travel to have the same kinetic energy? All right, so now they're saying if our kinetic energy is 147, so they're saying if our kinetic energy is 147, the same as the last time, but our ball is a different mass. So now it's only 60 grams. What was it before? 145. All right, so this is even less than half. But mass, got to move the decimal place 3 times for that, because there's 1,000 grams in a kilogram. So that becomes 0.06 kilograms. That's what I'll plug in for mass. And we want us to solve for velocity. And that comes out to be 70. And how fast would this 60-gram ball have to travel to have the same amount of momentum? All right, so we'll go back and see what do we have for a momentum initially. So our momentum was 6.53 initially. That equals mv. Our new mass is 0.06 kilograms. And so we're just going to solve for velocity. So 6.53 divided by 0.06. And rounding, that's 109. And so this problem is really just looking at the numbers. Since kinetic energy is v squared, where momentum is just momentum is just mv. So they're just trying to show you a comparison between numbers here. How kinetic energy is going to be much, much larger because you have velocity squared, where momentum is just velocity to the first power. So number 4, the magnitude of momentum of a cat is p. All right. So a cat has some momentum, is what they're saying. So it must be moving, has some velocity. What would be the magnitude of the momentum of a dog having 5 times the mass of the cat if it had the same speed as the cat? All right, so they're getting a little abstract here because we don't have any numbers. So they're saying the momentum of the cat is the mass of the cat times its velocity. Now, the momentum of the dog is going to be the mass of the dog. And now they're saying it has the same speed as the cat. So they both have the same velocity. The only thing that's going to be different here is the mass. And they're saying that the dog has 5 times the mass. So the mass of the dog is 5 times the mass of the cat. So here's my mass statement to indicate those words. And what do they want here? They want a ratio. So they want the ratio, just looking here at Mastering Physics right here, that it says P dog over P. So they want the momentum of the dog over the momentum of the cat. So the momentum of the dog is mass of the dog, but the mass of the dog is 5 times mass of the cat, velocity. And the momentum of the cat is just the mass of the cat times the velocity. And so the masses of the cats cancel, the velocities cancel, and we're just left with 5. So the dog will have 5 times more momentum than the cat. We look at part B. What would be the magnitude of the momentum of a dog having 5 times the mass of the cat if it had the same kinetic energy as the cat? All right, so we're going to have to write down some kinetic energy stuff here. So let's do kinetic energy of the cat. 1/2 mass of cat, velocity of the cat. Now I'm going to say velocity of the cat now because they're not saying the velocities are the same anymore. That was the previous part. It said the velocities are the same. Now they're saying the kinetic energies are the same. And so these would have to equal, well, that's what they're saying. They're saying the kinetic energy of the cat equals the kinetic energy of the dog. So that's this statement here saying their kinetic energies are equal, but they're also still saying that the mass of the dog is 5 times the mass of the cat. So I'm going to plug that in right here. So we would get 1/2 mass of the cat, velocity of the cat. And instead of mass of the dog, we're going to have 5 times the mass of the cat. And now these masses of the cats will divide out. These halves will also divide out. And so we're left with the velocity of the cat squared is going to equal 5 times the velocity of the dog squared. So that's what has to be true if their kinetic energies are equal. And they're still looking for this ratio. They're looking for the ratio of momentum dog over momentum cat. How do I know that? I'm just looking right here in Mastering Physics, this part where it's saying P dog over P. P is cat there, momentum of the cat. So the dog is velocity of dog, the cat. Again, the mass of the dog is 5 times the mass of the cat. The masses of the cat will divide out, so we're left with 5 velocity dog over velocity cat. And then we're going to use this relationship over here. So if I do take the square root of both sides, so if I square root both sides here, I get velocity of the cat is square root of 5 velocity of the dog. So I'm just taking this relationship we got from kinetic energy, square rooting both sides so we can get to v, just the velocity of the cat. And I'll just plug this in. I'll just take this velocity of the cat, plug it in right here. So we'd have 5 velocity of the dog over velocity of the cat, which I'm plugging this in. So that's square root of 5 over velocity dog. Well, the velocity dogs will cancel, and so we're left with 5 over square root of 5. And this will be interesting because sometimes they want us to rationalize the denominator to get rid of the square root. Let's see what mastering physics will do. Because I'm not going to rationalize the denominator. I'm just going to put square root of 5. And see what they say. And they'll take it, as they should. Rationalizing the denominator, getting rid of square roots, that's not wrong, but just extra work. Kind of a more simplified statement, though. But there we go. There is number 4. All right, so we got 2 figure skaters, and they're giving us their mass in terms of their weight. A little bit unfortunate, so we'll have to calculate the mass from that. Let's see, if the heavier skater travels at that speed, how fast will the lighter one travel? Oh, this is where they push off against each other. Okay, so this is where they're standing together. So there's my people. They're 2 boxes. They're just standing together. So the total initial momentum is 0. They're just standing together. And then they push off. And they go their respective ways as they push off. Momentum is conserved, which means the final momentum here is still 0 because momentum is conserved, so it has to be what it started at. However, now we have mass of this first person and their velocity, which is moving to the left, plus the mass of the second person, their velocity is moving to the right. So these have to add together to be 0. The minus sign will be in this first velocity here because you can see it's pointing to the left, this first velocity. And so let's see what we got. Our heavier skater. And, well, why don't I call M1 the heavier skater, and I'll call M2 the lighter one. It doesn't matter which here, just so I'm consistent through the problem. So I'll just call this one on the left the heavier one, the one on the right the lighter one. And we do have to look at these numbers here. So the weight, so the mass of the heavier person is going to be the 725 newtons divided by G. And then the mass of the lighter person, so I'm going to look here, 675 newtons divided by G. And I am just rounding that to the ones place there. And looking at our momentum statement, so the heavier person has mass 74. Their velocity is to the left, so it's going to get a minus sign. They're telling us the heavier skater travels at 1.4. The mass of the lighter person is 69. We don't know the velocity of the lighter person, but we know the total momentum has to be 0 because it's conserved. And so we can solve for the velocity of the lighter person by moving all this to the right side, which will make it positive. And we'll divide by the 69 to get us the velocity of the lighter person. and it's 1.5 to the right. They want to know, well, how much kinetic energy do these skaters have? Well, the heavier skater, I will say kinetic energy heavier, is 1/2. The heavier skater's mass is 74. Their velocity is 1.4. That gets squared. Plus the kinetic energy of the lighter skater, which is 1/2. Their mass is 69. And we just found their velocity is 1.5 squared. So I'm going to add these two together, my calculator. So just rounding that, you get 150, adding those two kinetic energies together. All right. Now we have a frictionless track. We got a glider moving at that speed to the right, collides with and sticks to another glider. All right. What is the net momentum of the two gliders before the collision? Very important. Right here it says the second glider is stationary. So we have this picture here. We have one glider that has a mass of 0.175 kilograms. And that was terrible. Let me try that again. That mass is 175 kilograms. Moving at 1.1. Moving to the right. And the other glider is stationary with 0 velocity. And its mass, the second one, is 0.27. So if we look at the total momentum here, we have the mass of the first glider times its velocity and plus the momentum of the second glider, but its velocity is 0. So 0 times that will get a 0. So here's the total momentum. It's all coming from the first glider. So 0.1925. So what must be the net momentum after the collision? Well, conservation of momentum says that that initial momentum has to be conserved. So the same momentum I have initially has to be the same momentum I continue to have. That's what conservation means, that the momentum is conserved. It's not changing. So now part C wants, what is the speed after collision? So here's our initial momentum. That's what stays conserved. We can write a new math statement for the final momentum, though, because now they get stuck together. When they get stuck together, that means we're adding both their masses together, because once they're stuck together, it's like they're one object. And so they're one object of this total mass. We'll add their masses together. That's their total mass. And they have some unknown final velocity. And this has to equal the initial momentum. And so we can find a final velocity by just taking this and dividing by the total mass. So again, the gliders get stuck together. When they're stuck together, it's like they're one object. It's like they're one object that has this combined mass. And then we can figure out the final velocity from conservation of momentum. Whoops. 0.43. in part D, is kinetic energy conserved during this collision? Now, collisions where things stick together, they're called inelastic collisions. Kinetic energy is never conserved for inelastic collisions, but you could check this out by comparing the different kinetic energies. So if we look at the initial kinetic energy of the system is 1/2 mv squared, where the mass is the glider and 1.1 is the velocity. So if we did look at this, that would be the initial kinetic energy. And now when they collide, there will be an energy loss when they collide here and stick together. So let's look at the kinetic energy when the masses are stuck together with this new final velocity that we had. And so here is the final kinetic energy. So the initial kinetic energy, 0.1, they collide, get stuck together. This final velocity we found right here. So I just plugged that in right there. And our kinetic energy is much less. So when things stick together, there's a lot of heating and stretching that consumes energy, and energy is not conserved when we have things stick together. So number 7, a frictionless surface as always. And we got a puck that has that mass towards another puck. We want to know what was the speed of puck A before the collision. So we're going to have to write some pictures here with the information given in this light blue box. So let's take a look at what picture we can draw here. We got a horizontal table. Puck A, there it is, has mass. And it's moving towards puck B. So I'll say puck B is over here, and A is moving towards it. Puck B has a mass of 0.4. which is initially at rest. So the velocity of B initially is 0 because it's at rest. Now there's a collision. After the collision, puck A is now moving to the left. So right here it says after the collision, puck A has a velocity of 0.12 to the left. So that's going to be minus since it's going to the left. And puck B has a velocity to the right. So this velocity, its final velocity here is to the right, so it's positive. And it's 0.65. So if we look at the initial momentum, so that's our first picture. If we look at the initial momentum from our first picture, we have the mass of puck A and its velocity. Puck B is not moving, has 0 velocity, so it has 0 momentum. And all we know for this first part is the mass. We know the mass is 0.2, but we don't know the initial velocity of puck A. If we look at the final momentum, so that's this second picture, we look at the final momentum, we have puck A and its final velocity, plus puck B, because puck B is now moving with its final velocity. And we know some numbers here. So the mass of A, 0.2. We know its velocity is to the left, so it's minus. And they told us that's 0.12. And then the mass of B, they told us, is 0.4. and a totals to final velocity is to the right, 0.65. So this is a number that I could type into my calculator, which I will do right now. So that is the total final momentum, and that has to equal the initial momentum because momentum is conserved, conservation of momentum. So we get this 0.236 must equal 0.2 velocity of the, so this right here. So the final momentum has to equal the initial momentum. The final momentum is a number. So here is the final momentum. It's this number that we figured out that has to equal the initial momentum. So we can just do 0.236 divided by 0.2 to figure out what the initial velocity of puck A was. That is 1.18. And in part B says, calculate the change in the total kinetic energy. All right, so I'm going to keep this paper because I need some of these numbers here. We're looking at the total change in kinetic energy, which means we want the initial kinetic energy of the system. So puck B is not moving, zero velocity, so there's no kinetic energy. No kinetic energy there. Kinetic energy is coming from this one. We just figured out what the initial velocity here is. It's 1.18. So the initial kinetic energy is all from puck A. It has 0.2 kilograms, and it was 1.18, and that's V squared. That's a V squared, so 1/2 mv squared. That's the initial kinetic energy. Let's look at the final. The final is going to be puck A. So puck A is moving to the left. So puck A has mass 0.2, moving to the left. And I did put a minus sign in there. It doesn't matter because it gets squared. So minus squared will be positive. But in kinetic energy final, puck B is also moving. So we have to include that kinetic energy. Puck B had mass 0.4, and its velocity was 0.65, and that's squared. So let me just figure out what these numbers are here. And then what kinetic energy final, I'm going to type all this number into my calculator then. All right, so there's our final. Now they want the change in kinetics. So looking at part B, it's got delta K. That means the change in kinetic energy. So the delta symbol is always defined as final minus initial. So the final kinetic energy we got was 0.0859 minus the initial is 0.139. And so kinetic energy was lost. And that is number 7. Number 8. What do we got here? 750 kilogram car is stalled on an icy road. Another car is traveling eastbound, and collides with the rear of the stalled car. After being hit, the car slides at the ice and at speed in that direction, north of east. All right, so north of east means we're going to be dealing with two dimensions. Let's start drawing a picture to help us out. So we have our car stalled and 750 kilograms. It's got initial velocity of 0. It's just hanging out. Actually, I need to do a top down. Because we got two dimensions here, it says north and east. I'm actually going to need to do a top down picture here. So bird's eye view, we're looking down on these cars. So here's our 750 kilogram car. It's just sitting there. Another car is cruising along at 1,000 kilograms going east, it says, eastbound at 15 meters per second. So we can get the initial momentum here. And because we're looking top down, we're dealing with two dimensions. So the x direction, no momentum from the stalled car because it has 0 velocity. All the momentum coming from the car here. So mv, the mass of the car is 1,000. 15 is its velocity. So we have a total momentum here of 15,000 in the x direction. Now there's no momentum in the y direction here because the car's moving strictly in the x direction. So there's no momentum in the y. And then the cars collide. And it says the 750, so here's my second picture. So the 750 is now going 30 degrees north of east. So here I am north of east. And at 4 meters per second is the final velocity of the second car. I'm going to call this the second car, call that one the first one. And what else do we got? So the second car is off here somewhere, 1,000. Looking at our momentums in the x direction. So the car, 750 mass. Now its velocity in the x direction is just this component here. Here's the velocity in the x direction. The adjacent leg of this right triangle, we'll get the adjacent leg from cosine. So cosine of 30 degrees will equal our adjacent over the hypotenuse, which is 4. So 4 cosine 30 is the momentum from this car. And there must be some momentum from the other car in the x direction. And we want to know, well, the first question is, what is the magnitude of the velocity of the 1,000 kilogram car after the collision? So we're trying to figure out what happened to this other car. It's kind of cruising off this way. So let's look at some angle here. And I'm just going to take this statement. I wrote it a little bit too close to the end of the page there. Let me rewrite that one again. So from the first car, 750, its x component and then the second car has its mass, which is 1,000. And now its component is presumably going to the left, so they collided. This car going to go to the right. And we actually don't know. Maybe this car will just push through. Maybe it'll bounce back off. But there's some x component to this velocity here. Not quite sure what that is yet. But we know the initial momentum of the x direction has to equal the final. So we can get this final momentum in the x direction is going to equal this initial in the x direction, 15,000. That'll allow us to solve for the x component of velocity from the other car. If we look at the final momentum in the y direction, now in the y direction we have this component, the opposite, that's the y component there. What gets us the opposite is cosine. So for the 750 kilogram car, it's now sine 30 for the y component, plus the other car that also has its y component. And we know the velocity in the y direction has to equal 0 because momentum is conserved. So again, our first picture here, we got the initial momentum in the x direction right here. We got the initial momentum in the y direction here. And that has to be conserved. So here is again the initial in the x direction and the initial in the y direction. And then from these two, we can figure out the x component and the y component. So let me write down the x component first here. So that'll be 15,000. And we're going to take all this, move it to the right side, so that'll make it negative. And then divide everything by 1,000. That would be the x component of velocity. Looking at the second momentum equation, we want to solve for Vy. So I'll take everything here and move it to the right. That'll make it negative. And divided by that 1,000, that'll give us the y component. So I'm going to type in both these numbers here into my calculator. So we get the velocity x. So the car actually did push forward, but went down. So, well, before I draw that picture, let me just answer part A here since I have these two numbers here. So part A wants to know what is the magnitude of the velocity of the final car. Well, once we have two components, so the car has some overall velocity, and that component is a positive x, which we figured out to be 12.4, and this minus 1.5. So this forms a right triangle. We want to get the hypotenuse. So using Pythagorean theorem, we can get what the hypotenuse is. And then we'll square those, take the square root. So the final total velocity would be 12.5 there. So let me just draw this picture out here because I've run out of space. But let me draw a better picture here. So the car, the 750 car, is going off at some angle 30 degrees. Now we don't know what happened initially with this first car. I drew it kind of going like this, but I let the math solve its numbers out. Now that I'm looking at the numbers, we have a positive x component, but a negative y. So that means the second car, and when it hit, it's still going to the right at 12.4, but it's also going down. That means the second car is going off like this. It's going down minus 1.5 and to the right 12.4. And then the final velocity then, the total velocity of the car is these two components with Pythagorean theorem. That's how I got the total velocity there to be 12.5 from Pythagorean theorem of that right triangle. That's the 1,000 car there. And they want to know what is the angle here then. So we can get an angle here. I just stick a theta there. So that would be opposite and adjacent. We can use tangent there to get opposite over adjacent, and then use arctangent on that. So that'd be 83 degrees there. They do have, so just looking at part B, they have all this in bold here. Let me just see what that says. Express your answer in degrees measured from the east. Measure from the east direction. All right, well, I measured from the south here. So I got this angle. East is this way though, so they're asking from the east, which means they want this angle here. Well, that's 90 degrees. We figured out this is 83, which means this is 7. Oops, there's that picture. So the angle I got for my triangle, this one's actually measuring off south, 80 degrees south, east of south. They want this to be measured from the east direction. So 83 and 7, 90 degrees. That's how we can figure out this is 7. So it's going 7 degrees south of east. And it says enter positive if it's north of east and answer negative if it's south of east. All right, I am south of east, so I'll put in a minus. And I got that angle to be 7. And then finally for part C, they want the ratio of kinetic energy of the two cars just after the collision to that just before the collision. Okay? So they want the total kinetic energy initially of these two cars. And let me just go back to my original piece of paper on that. So originally, the 750 is sitting still, has no kinetic energy. So all the kinetic energy is coming from the moving car. So the initial kinetic energy of the moving car is that had a mass of 1,000 and it had a velocity of 15. So that's the initial, there's the initial kinetic energy. The 1,000 kilogram car was moving at 15 meters per second. The other one was just sitting still. So here is the initial kinetic energy. And then let's look at the final. Now in the final, both cars are now moving. So let's look at the 750 car. So that was this one right here. And what velocity was that moving at? 4. They told us this hypotenuse was 4. So that is the velocity of the car there, 4 squared. And then plus the 1,000 kilogram car, so plus 1/2 mv squared of the 1,000 kilogram car. And the velocity of the 1,000 kilogram car we figured out to be 12.5. So this is going to be 12.5 squared. And here's the final kinetic energy. I'll type into my calculator. All right. Now, they don't want to change in kinetic energy this time. They're actually asking for the ratio, and I had to look closer. That is final over initial is what they're asking for. They're asking for final over initial. So final, I have 84125. The initial is 112,500, and I will type that in my calculator. to be 0.75. I did round that to the second decimal place there. There is number 8. All right, number 9, we got a 4.25 gram bullet. All right, so we got a bullet. I'm going to immediately change that mass to kilograms. So we'll divide by 1,000, means to move the decimal place 3 to the left. So 1, 2, 3. And has a velocity of 375. Initial velocity there. And it's fired into a wooden block that has a mass of 1.2 kilograms. So here's our wooden block, 1.2 kilograms. Its initial velocity is 0, though. Just hanging out. And this is all on a surface. The bullet passes through the block and emerges with its speed reduced to, what does that say, 118. So that's picture 1. Picture 2 is the blocks here. The bullet now has a final velocity of 118. So if we look at the initial momentum, it's m of the bullet times the velocity of the bullet. Oops, 375. And the momentum of the block is 0 because it has velocity 0. So I'll type this into my calculator. That's the initial momentum. Let's look at the final momentum. Final momentum is, again, the bullet that has this mass. Now the bullet is traveling 118. And the block has a mass of 1.2, but we have no idea what is happening with its velocity. So I'm just going to put a math variable there. Conservation of momentum says initial has to equal final. So the initial momentum of 1.59 would have to equal this final momentum. And then we can solve. So I'll do 1.59 minus this. And then finally divided by. .91. And I did get a positive value here. So that means when the bullet passed through the block still has a little motion to the right. And the last one. All right, we got a chunk of ice sliding at that speed on the floor. Everything's ice, so it's frictionless. Collides, sticks together with another chunk that's initially at rest. Why don't we draw that picture out? So we have this one is moving, and this one's at rest. And both these chunks are the same mass. So if we look at initial momentum, we have one block and its velocity, and the other block has 0 velocity. So here is our initial momentum. And then they stick together. So now they stick, they're like one mass. So we're adding 4.75 together then to get the total mass. So now the total mass here will be 9.5 kilograms as they're both stuck together. And now it has some velocity. So the final momentum will be this total mass of them stuck together with some unknown velocity. This has to equal the initial momentum, which we just figured out is 52.25, so we can figure out the final velocity. So the final velocity of these chunks together, 5.5. And let's see what it says here. Part A says, how fast are they moving when they reach the valley floor again? What do they mean? So let me just see again. They collide, they stick together. The valley's icy, there's no friction, okay? After the collision, the blocks slide up the hill and then slide back down, okay? So our blocks collide. So here's the blocks are now stuck together with this velocity. So the block goes up. It doesn't have enough momentum to get over the hill. So it falls back down. And the only thing that's changed here is the velocity is now in the negative direction. So there's no energy loss. There's no external forces because it's on ice. So momentum is still conserved. The momentum it had here initially is still going to be the momentum it has when it comes back. It's just not, now the block is moving to the left. So to the left means it would have a minus velocity. And I'm curious if they require the minus. I mean, they should. That's the only difference. What if I put in a positive value? Well, it takes it. So that's a little unfortunate, but when they're stuck together, it's got a positive velocity this way, goes up the hill, can't quite make it, so it comes back down, now going in the negative direction. So technically should be a minus there, but there is number 10, the last of the practice homework.